So let's get started, I guess.
Yep.
Yeah, it doesn't look like anybody else is joining.
So today we will be talking about the n-step bootstrapping approach. And this is a generalization for Monte Carlo and temporal difference methods we considered already. And essentially this gives us like a framework to talk about something that is in between of temporal difference methods and Monte Carlo methods. And here is the authors mentioned that usually this is used as introduction to the eligibility traces idea. We will be viewing at chapter 12. And yeah, actually, this kind of n-step bootstrapping methods are usually implemented using this eligibility traces, not like we will be doing in this chapter, but here we can familiarize ourselves with some like theory behind it. And with that, let's move to the n-step temporal difference prediction. And this backup diagram should give us a good understanding of what we're dealing with. Here is a one-step temporal difference method. And that is something like we dealt with before, right? So we just look one step ahead. And there are, but we can, what we could do this look ahead to multiple steps, right? And in the extreme case of that would be a Monte Carlo method when we look through all of our experiences up to the terminal state. And from this backup diagram, it's evident that the limitation of Monte Carlo method is that we need to reach the termination before we do any updates. And the kind of limitation of one-step temporal difference method is that we don't have like too much of we are dealing with a short horizon in the future, right? So we are looking only one step ahead, and what we can do, we can do something intermediate, like take an arbitrary number of steps and use that number of steps to bootstrap our state or action or whatever value function. So let's look at the formulas. How does all this stuff work? So our one-step return is defined just as a sum of the reward at step t+1 and state value function estimate for state t+1 discounted by factor gamma. And what we can do, we can unroll this to take basically any number of steps, right? So here is a version for 2 steps. Here we look ahead 2 steps forward, right? So we to estimate the return for time step that we are going to use for basically bootstrapping at time step t. We will look at the reward at time step t+1 and discounted reward at time step t+2 and state value estimate for the final state we are like looking ahead for. And here is a generalization of that written in terms of n, where n is the number of steps we are looking forward. And the update for n-step bootstrapping is given as basically we use some like a factor alpha, which can be interpreted as a learning rate, or like a how much weight do we want to put on the update on the new experiences. And we use this return minus our current estimate for the value of state t, right? And in this way, it's again, it's very similar to what we saw before, but the way we compute this value of expected return is a bit different, right? Okay, and here we get to the first exercise, and yeah, in chapter 6, we saw that Monte Carlo update can be written as a sum of temporal difference updates or errors, and if we assume that value estimates don't change from step to step. And so the where is this change from step to step of value estimate is in this formula? It's here in this part, right? So we use Wes estimate for a state value for like which is actual at time step t plus n minus 1, right? And we use it to compute like our estimate for the next time step. But if we assume that the value estimate do not change over the course of experiment, then the n-step error can be written as a sum of temporal difference error. Oh, okay, let me just reshare my screen quickly. I will just go with everything, and so here I done the derivation, and the derivation is essentially it's very simple, and it uses this assumption that value state value doesn't change. So we drop if we can drop this indices for the state value function, then we can recursively factor out the TD error. Here it's written as delta sub t, and then we can recursively factor out the TD error for each of the time steps. Here you can see that first we factor out the TD error for time step t, then we can factor out the TD error for time step t plus 1, which is here, and it's discounted by factor gamma, and so on. And finally, we got to the point where this discounted value estimate for the time step st plus n cancel out, and the TD error becomes a sum from for k equals t to tn plus 1 plus n minus 1, and the sum of discounted TD errors. Okay, so let's go back to the book. Yeah, and with n-step method, the next exercise, with n-step method, the value estimates do change from step to step. So an algorithm that uses the sum of TD errors in place of the error defined in 7.2, so this one, will be slightly different. And would it be better or worse? And I haven't done the programming for this exercise, but I think we can safely assume that it will be worse algorithm, because in this case, so what we will have to do, we will have to store the TD errors at each time step, and then use those for our update. But in that case, we are not using the latest estimate of the value of the state value function, but we are using the estimate for state value function available at the basically at time step t when the action is done, and that would be probably less efficient, because we assume that with time our state value estimate is improving, right?
Mm-hmm. No, won't it be dependent upon the value of n too, n or t? I mean, if we have those parameters that are suitable to the particular case in which the suppose our first type of algorithm is more suitable to a particular way of calculation with respect to here. I think so. They have estimated the values before they have actually done the calculations for the value estimate. So I was thinking if we reverse this or make some changes to it, wouldn't it affect the way our algorithm is designed here? I mean, as you alluded to with respect to the changes here in the box that you said here in the second half of the cursor, the three lines that you have above the cursor. I was referring to these. Yep.
Yeah, so here what we will have, instead of this computation, right, we will have a sum of the TD errors stored at the time step t, because in that case we are kind of disregard the fact that the value estimate change, right? So we are just taking the TD error for whatever value estimate we have at time step t, right? So that's my understanding of the difference here. And in that case, so basically this part will become irrelevant, because we have this value TD errors stored, and we just sum those for the horizon, like from t from tau plus 1 to tau plus n, and then we just use that for an update, right? And
yes.
yeah, and assuming basically assuming that each of our updates in expectation is taking our state value function towards the actual state value function, this kind of update should be better compared to that one when we use like the state value function available at time step t. So, but yeah, it would be interesting to try that out, and yeah, that wouldn't take too much of effort, but yeah, I haven't done that yet.
Cool. It's interesting to speculate here, because I think so. There might be cases. I think in the next page they have given a figure with respect to the n values and the average RMSE errors. The percentage between this is the figure that I was referring to. So I was thinking here they have taken 19 states. So what happens when we play with the number of states and with the n values, and there might be some algorithm that might help in the first case versus tuning of we can say here hyperparameters, which might help with the second or the third case that we might have. So I was thinking from that perspective.
Yeah, I guess so. That may be in some cases, but yeah, overall it would be interesting to try that out and try to maybe come up with an experiment or like problem statement that will favor this first algorithm rather than the actual one. But in general, I would suspect that if we are given this algorithm as a reference, that one would be better, like in expectation. So that's just with that intuition as well. But yeah, as you can see, there is a lot of stochasticity to all this stuff, and in some cases, the behavior is kind of hard to predict.
And one more query with respect to, since this is a purely tabular case, what will happen in the case of some connets or some approximations that we do? How will that affect this kind of a n-step bootstrapping process? There we might see a completely different result based on the feature approximations that we select. So we are in that case, and depending upon the algorithm that we choose or the type of implementation that we choose, we might have some other results too. But here we are only considering the tabular cases. So that's one of my tangents too.
Yeah, I was thinking about this like a problem of choosing a proper like experience buffer, right? We have this in practical cases, we are usually using some experience buffer, and the older experiences are usually generated with outdated policy, right? And yeah, I'm really curious about how this all is done in practice, but hopefully we will get to that later when progressing through the book, and maybe we'll get to the point when we can discuss some relevant papers which are coming out recently, and yeah, so that would be really interesting to look at. Yeah, basically, I think right now we are building the theoretical and intuitive ground for understanding the design choices done in the actual algorithm used in practice. So we haven't got to those yet, really.
True.
Okay, so now let's look in more details through this example. And the problem formulation is here very similar to what we saw in chapter 6, which is a Markov reward process. And we don't have any decisions here. So there are two possible actions, go left or go right. And the actions are taken randomly, and the rewards are only the rewards for all transitions is 0, but there are non-zero rewards for the terminal cases. And in this example, it's -1 for the left terminal state and 1 for a right terminal state. So basically we do the random walks starting from the center of some, yes, starting in the center, and then we do a random walk and we can end up in the left or in the right terminal state, and we get a reward of 1 if we end up in the right, and -1 if we end up at the left. And the task here is to estimate the state value function for this for the state. And here we use 19 states instead of 5 that were used in the first similar example in chapter 6. And why do we do that? Because we want to demonstrate how the how this n-step bootstrapping works, and it wouldn't make that much sense if our experiences are rather short on average. So it doesn't make much sense to use like 16-step bootstrapping for this problem setting when we have only 5 states, because we can do, if we do like 3 consecutive steps to one side, we are done, right? And the average length of the experience would be probably something around, I'm not sure, but it can be calculated, and it wouldn't be too long. So the values of n over to this side wouldn't make that much sense. But also, as you can see from this plot here, the values for n that are higher do not work that great. And the best value is for this particular problem is here with n equal to 4, and the alpha is just below 0.4. Okay, and here are some questions. Why do you think larger random walk task, 19 states instead of 5, was used in the example in the chapter? Would a smaller walk have shifted the advantage to a different value of n? And how about the change in the left side outcome from 0 to -1 made in the larger walk? And do you think that made any difference in the best value of n? Yeah, and I have an implementation for this task with a small modification. So in the book, they use, so they average over first 10 episodes. And what I did, I took the estimate, the state value estimate after 10 episodes. And with that, let me get back to the 19 states. With that, let's wait till it computes. So the best value I've observed here, as you can see, is 16. And yeah, it would take a bit longer if I add another value for n, and I've cut off at 16 because in the book they show that like the 32 already performs significantly worse. So here, why this plot is different from what we see in the book, because I take the final estimate for value at time step or after 10 episodes, instead of taking the average over all 10 episodes. And like intuitively, the difference is here because with larger values of n, we will update, like we will basically we will propagate the updates early in the training too far, so that those updates would be kind of irrelevant for the states we are updating, and that can result in a slightly worse training early. Okay, and regarding the question, how does it depend on the number of states in in this random reward process? We can have a look, for example, for 7 states. We have different best, and that would be either 2 with alpha 0.45 or something, or 4 with a lower alpha, like 0.25. And as you can see, it that in general, this rule holds that for longer, like with a larger n, we need a lower alpha. And also it would be interesting if we try, I haven't tried that yet. Let me see. What if we discount the rewards? So in this example, we do not apply the discounting, but what we can do, we can set gamma to be 0.9 as it is done, and let's see what we will get in that case. And interestingly, in this case, the best performance is observed with n equal to 1. And yeah, let's have a look at larger number of states.
Here you have fixed discount factors 0.9.
So Okay, and looks like everything is kind of smoothed out, and with gamma, the discount factor of 0.9, we can see that we can use a higher alpha, right? So this is alpha here, the x-axis. Probably need to set it. And you can see that in this case, the value 2 for with high alpha performs reasonably good, and value 4 with moderate alpha performs good. Yeah, that's something to play around with. And yeah, another thing I wanted to try out here was like to have a look at the, so this is a history of how the values are updated, and this is using the regular TD method. So you can see that at each, so here is a value estimates for time step 0. We start with zeros here everywhere, and then we use alpha of 0.1 here, and after first time step, like only one state value estimate is updated, and then another one, and then maybe another one, and so on. Okay, and yeah, the n step TD with n equal to 1, yeah, that's the same, right? As a regular TD update. But let's try to increase n and see what's going on. And you can see that with that, maybe let's also, yeah, that's fine. You can see that we have less 0 values after 2 time steps here, and with 3 we have even less, and with 4 we already have a lot of values updated after the third episode, right?
Yep.
Unlike in the case of one step TD. So that kind of speeds up the learning, and that, I think that gives an intuition of how does it work. Okay. Yeah. So any additional comments or questions on this example, and basically what do we make of it?
Sorry, your initial values there, were they all set to 0?
And initial values for the state value function are all zeros, right?
Yeah, like I think in the text, does it say he sets them to 0.5?
That was for the previous. Recall that estimate values of the all states 0.5, but I think in this experiment he
Oh
said,
yeah, it says, yeah. He says he set them to 0. Sorry. Yep. Okay.
Yeah, so I think it's like it's set to mean of the like of the 2 rewards, right? And that would be also a mean of the states. Yeah.
Yep. Okay.
Yeah. So, and we can try and see what will happen if we change that as well, if you'd like. let's do that. Here I will set it. Okay, I have here it set to the mean, and let's say make it 0.5 and run the experiment. So I removed the discounting and added this initialization that is different from the mean of the reward. And you can see that in this case, it looks like the learning with higher values for n perform worse, right? And that make some intuitive sense because we have like this initial bias in our state value estimates, right? And the higher n we have, the further this bias is kind of propagated, right? So I would guess that that's how it works, but yeah, that just my thoughts on it. Okay, and here just to contrast it, let's look again at the values with 0 initialization. Oh no. Okay, so something was also different here. So here again we observe that yeah, it's very similar. Okay, so what else have changed? I'm not sure. I think we saw different results before, right?
Yep.
That's interesting. I will check what might be the reason
But
for it.
yeah, the results are pretty much on the same. The patterns are the same. I mean,
yeah, so that's something to play around with a bit more. Yeah, the patterns hold now. So okay, maybe there is something that is propagated in some weird way from somewhere else, but whatever. I think that we should have a good understanding of how this works overall here now. Yeah. Okay, so now let's move to the n-step control. And the first algorithm we will be looking at is n-step Sarsa. So as you remember, the Sarsa algorithm introduced in the previous chapter, we used the Q or action value estimate for the state action per a or t+1 to bootstrap the update for the state for the action value estimate at time step t. So here, and here we will use this value for the estimation of the expected returns, and this is very similar to the expected returns we used for state value estimate, but in this case we use, instead of v of s t plus n, here we use q of st plus n at plus n, right? And that's all we changed, and the update is done just like before as well. So we we use that difference. So this is our n step TD error or n step error for the update. It's here, right? And we can look at the backup diagrams for all the variants we have here, and just as well as with TD prediction, it's very similar. So, and the new thing here is n-step expected Sarsa, and you can see that it's very similar to the Sarsa again, but except for the last step here, where we take the expected value instead of the sample.
Yep, and we have a large variance there in the case of expected Sarsa.
Large variance?
Large variance in the sense we are not doubling down on a particular value, like in Monte Carlo updates, which go down a particular terminal. A particular terminal state. So here we have a variance of the backup. If we kind of like view it from implementational perspective, this Monte Carlo and expected Sarsa are two opposite ends of the bias variance curve that we can draw in. These will be on the opposite ends of the spectrum. I think you guys are getting my point. With respect to the practical implementation and the differences between the Monte Carlo and the Sarsa.
Yeah, I guess that. So let's have a look first at how expected Sarsa is different from regular Sarsa in terms of formulas here. So for the n-step Sarsa, we had the q sub t plus n minus 1 of st plus 1 plus n, at plus n. And for the expected Sarsa, instead we use this v bar, which is called expected approximate value, right? And the expected approximate value is just what we had before for Sarsa. So it's a sum over all actions for state S, right? A sum, a weighted sum by the probability of action times probability of action times the Q of state action pair, right? And that's how it's different mathematically from the regular Sarsa. So regular Sarsa was given here and in 7.4, right? And we had a sample. So we use action value estimate for action 80 plus 1, which is a sampled action, right? And here we use this value called expected approximate value of state S, which is just an expectation of the value for this state, right?
Yep, and hence the large variance that will be we will have here as opposed to the Sarsa that I was.
Yeah, I'm not quite following how taking the expectation instead of a sample results in larger variance. It occurs to me like it should be opposite way, right? So when we take a sample, we have a high variance, and when we take expectation, we have a lower variance, right? I'm not quite sure how it. What do you mean?
What do you think, Steve?
I would have agreed with what Ardo said there. Yeah, like I thought taking the expectation would sort of reduce the variance because of the fact you are like averaging over the various actions at the end as opposed to just choosing one.
Yeah.
Why do you think
Okay.
the variance increases?
Because it's averaging over the 4 or 5 values that it had. So I think so. If we calculate the mean, I think that will give a mean versus the versus the normal Sarsa, where that will give us the sampled estimate. So the sample estimate will be will actually point to a particular value, whereas the expectation might give us a mean of it with respect to the range that we have. Range here, it might have suppose 3 or 4 different values, and the expectation might give us a mean here, or I'm confused. I don't know.
Yeah, let's imagine a situation when we sample, so regular Sarsa, and let's say we have 2 possible actions. And according to our policy, pi, one action has probability of 0.95 and another of 0.05, right? And that's like when we have this epsilon greedy strategy, right? But in case of Sarsa, it is possible that we sample the action which is of low probability here, right? And in that case, we will use the action value estimate for that low probability action. And in case of expected Sarsa, we always take here for that for those 2 actions, we take 0.95 of the action value for action for the probable action and 0.05 for non-probable action, right? And imagine the situation when we sample when we sample the non-probable action multiple times, and that will basically, even though the expectation remains the same, it will shift our, or like, I think it will increase the noise in our update because we just rely on this low probability action, or we take into account this low probability action multiple times, even though it's really, it shouldn't be that much of a concern for us because we are interested more like so the value for the state t depends more on the action value that is corresponding for the action value for t+1 that corresponds to the more probable action, right?
Yeah, that's what I would have thought. So like I'd have thought, yeah, your return there in the normal Sarsa case varies between the minimum Q value and the maximum Q value, giving like a large variance, whereas like in the expected Sarsa, it's always a mean between the two, so the variance will be reduced.
Yeah, and I think that what we observed with some like examples there, so that the like the solution to which expected Sarsa converged were more stable compared to what we observed with regular Sarsa. There was some variation for the solutions found by Sarsa.
Yeah, this clears things up. Thanks, guys.
Cool. Nice. And okay, so here is an algorithm. So we haven't looked in the details into the first algorithm, but basically this one is very similar. And let's just walk through it. So this is the first like control algorithm for n-step bootstrapping. Let's walk through it line by line and understand it. So what do we need to run Sarsa? We need to initialize our queue action value function for all states and actions. And then we initialize policy and we basically at this point in time we kind of initialize all this stuff randomly. So we can start with a random policy and a queue initialize with some constants as we saw before. And we have following parameters for this algorithm. We have a step size alpha, and we saw that there is a significant impact of alpha on the results in this n-step bootstrapping case from the previous example. Also, we select an epsilon, which so in the chapters we viewed so far, we always use it as a constant. And I was wondering, why don't we kind of try to anneal it over the course of training? But yeah, apparently that's not as interesting because you need to select some way to like, so the annealing schedule will be kind of some kind of guessing, and it kind of disables the learning in non-stationary environment and stuff. So probably that is why we do not consider some epsilon schedules. But overall, this epsilon is a measure how exploratory our policy would be, right? So we select an epsilon greedy policy, or keep our policy epsilon soft. And the value for n determines the number of bootstrapping steps. And so something to notice here, that we need to do all the, so we keep a buffer of previous states, actions, and rewards. And this buffer of size n+1, and that is why we do all the indexing modulo n+1. Does it make sense to everyone? So we need to do the update for any time step tau. We need to consider next n state action reward triplets, and for that reason we need to store n state action reward triplets. Yeah, we could keep this buffer size at n, but it's handy to have it n+1 so that we store the current values as well. So and this keeps us have these two parts disentangled. But yeah, overall we need to store the we need to have an access for n values to do an update. And yeah, and then we proceed in loop. We do multiple episodes with the following sequence. We initialize some state, and we can select it randomly, or we can have some like stationary initial states or set of possible initial states. Doesn't matter. It depends on the problem, but overall we just select some initial state, and we sample the first action according to our policy here. And yeah, so the first action is not meaningful. It's sampled from the a newly initialized policy, which has nothing like it at the very first time step. But after first episode, we will be sampling this action accordingly to the policy learned during the previous episodes, right? Okay, then we do the following loop. So here we loop over the steps in the episode. And what we do is we take action and observe the reward and next state. And if the state is terminal, we set this T capital, which is basically our time of we can call it a time of termination, right? To be T+1. And if we haven't reached the terminal state, we will sample the next action. And that's basically it. And we store this R and S in that buffer we will use here. And here we will, so tau is a state that is being updated. And here you can see, for example, if we set n to be 4, and we will not update any values for a value for any state before we get to time step 3. Yeah, because before that tau will be less than 0. So once tau is greater than 0, in other words, we have enough experiences to do the n-step bootstrapping, what we do, we sum the discounted rewards for all the n future steps, right? So we start tau plus 1 to tau plus n. We sum all the rewards. Then we add, if this final the final time step we're considering is not terminal, then we add a discounted action value estimate for the state action pair for time step tau plus n, and we do an update for the state and action pair tau. And we learn the policy pi, so we need to make it epsilon greedy with respect to current newly updated Q, right? So we need to update a policy only for this state, so tau. And we do that until we reach the end, until our updated state is not a terminal state. So we obviously do not need to update the value for the terminal state. Okay, and because the value of the terminal state is usually constant. So that's, and here is an example of how it works. Imagine we are in a grid world here, and we are moving. So here's our path towards some location with the reward marked as G. And in case of one-step Sarsa, we will use this G only to update the previous Q value for the previous time step, right? And to propagate it further down this sequence of actions, we will need multiple iterations, right? So like next time we will be taking this path, the high reward from state G will be kind of propagated through this previous time step to this time step and so on. But in 10-step Sarsa, we propagate the high reward from a state G all the way down through the 10 previous states. So we kind of count the reward observed, discounted reward observed at state G through all these states, right? And that is why so we will do much more, or precisely 10 times more updates to our action value function compared to the regular Sarsa.
Yep, it's like it is 10x the regular one-step method. It's like when you have n step, then you have in the third figure that we can see. It's like we can see the small arrows here, and these arrows reflect the number of steps that this third part of the figure had. Here it is a 10-step Sarsa, so 10x the return, or which leads to a high reward. So it's like it's accumulated by that, as they have displayed in the figure and have written it down in the text too.
Yep. And here in this particular line, you can see how the reward for time step tau plus n is used for the expected return estimate for the time step tau, right? So you can relate this line here to this picture here. Okay, and let's go further. Prove that the n-step return of Sarsa can be written exactly in terms of null TD error as and this equation given. And you can do this proof exactly as I showed for the previous case by just doing a substitution here. So that is kind of how it works. You can substitute the values and refactor it and get the TD errors and define the expected returns in terms of TD errors. Okay, and yeah, we have already looked into this. The expected approximate value for a state action pair S and A under policy pi, right? Okay, now let's move on to off-policy learning. And here, how can we do the off-policy learning? And consider the case when we want to learn policy pi while acting according to the behavioral policy B, right? And why we might want to do that, we have already talked about it in the previous chapters, that in some cases it is kind of our experiences are given, and but we want to learn a better policy, and there are also sometimes we want to learn a greedy policy while having our behavioral policy exploratory, right? And that is obviously that was nicely highlighted in that Cliff Gridwald example, when we wanted to learn a greedy policy, but the exploratory policy was giving us kind of this high negative rewards, which will not ever be observed if you follow a greedy policy. And the way to do off-policy learning with this n-step bootstrapping it is done using importance sampling. And you can remember importance sampling from the Monte Carlo chapter, I guess. It was introduced somewhere, and that is like a common, widely used technique. And in brief, and for more detail, it was explained in more details in that Monte Carlo chapter. So we will weight our updates by the ratio of probabilities of action. Here you can see that we take a product from T to H, which here H is kind of our horizon of the ratios of probabilities of action K and the policy pi, which we want to learn, over the probability of action K and the policy B, which is our behavioral policy. And in this, what this ratio would be. So imagine our pi is a greedy policy, then all the probabilities except for the probability of greedy action will be 0. And imagine our behavioral policy is, say, epsilon greedy policy. In that case, we will have non-zero probability for the non-greedy actions. But this, how it's called, this multiplier here, it will just zero out the contribution of the returns observed after taking non-greedy action. And it will amplify the contribution of the return of greedy action, because we will have a 1 for greedy action here and something that is less than 1 for the greedy action here. So we will have actually some kind of multiplier here, okay? And as you can suspect, this will increase the variance of the update, yeah? So because in many cases, we will have a 0 here. Every time we take non-greedy action, we will zero out the update, right? And yeah, here you can see the equation for n-step Sarsa of policy variant of n-step Sarsa, and it's just the same as before, but with action value function instead of state value function. Okay, and in terms of algorithms, we will have another policy to keep track of. So we will have our greedy policy and our behavioral policy. And the behavioral policy should be such that probability of all actions at all states is non-zero, right? And that is needed to ensure that we explore all the possible states. And we will need to keep track of this value rho, which is our importance ratio. Okay, and so there was a problem that many of these experiences here are zeroed out by a rho when we have a non-greedy action. So but it will actually kind of exclude a lot of experience from learning, and also it will increase the variance. And there is an alternative here, and it's called per decision methods with control variates. So the control variate, it is this value here. It's this will make sure that at each time step our return estimate is not zero, and it is a linear combination of rho and rho is a product of probability of our probability ratios, so it's always between 0 and 1, right? And or not. Would it be always between 0 and 1 or not?
Yes.
Yeah.
Mm-hmm.
So cool. And therefore we have a linear combination of these two values, and here the second term is called the control variate, and the authors mentioned that there is no obvious reason why it's called that way. So that is interesting. And this method is supposed to increase the data efficiency of the learning algorithms. And yeah, it would be interesting to experiment with it, and I think we have a task here to do this, to run these experiments, but I haven't implemented that yet. Okay, but yeah, I think that would be an interesting experiment to try out, and I will do it and maybe show during the next session what the results would be. Or you can probably find it in any of the implementations available in Python or Julia or whatever your preferred programming language is. Okay. But let's move on to the next topic, which anyway, the importance sampling kind of introduces some kind of noise to our learning experience, right? So we drop a lot of experiences because those are not to be observed under the actual under the learned policy. And alternative to that is tree backup algorithms, and that is another way to do off-policy learning without importance sampling. And here is a backup diagram for this tree backup algorithm. And we have 3 steps here. And in this case, we will do what we will do. We will take the, so it is in a sense very similar to expected Sarsa if we would take an expectation for at each time step when doing the bootstrapping, but there is a certain difference, and we will look at it in the formula here. And let's see. So here is one step Sarsa, right? We estimate our expected returns as a sum of a reward and the expected value expectation over all actions of q at st+1, right? So let's expand it to 2 time steps. And now what we will do, we will sum over all possible actions at time step t+1 except the actual action we took, right? And why? Because we will have the outcome, actual outcome for our action we took, right? It doesn't make much sense to include the estimate, the current estimate for that state action value for st+1, at+1, because we will have actual outcome for st+1, at+1. That's the action we are actually doing. And here it comes. It will be weighted by the probability of that action times, and again this is very similar to the expected Sarsa, right? And yeah, and we can do some refactoring, and this can be written as a sum of 2 components: the expected the expectation over all action except the action we actually took, plus the returns for that action weighted by its probability. Okay, and that is actually the weighting by probability makes sense because we in that case we can kind of have an expectation here isn't changed, right? The expectation of all this component, and we can generalize it to n steps in the same way, just sum of over all possible actions we did not took plus the expected returns for starting from a next timestamp, but weighted by its probability of an action that took us to the state. Okay, and here we have the update equation for that algorithm, and once again this can be rewritten in terms of TD errors, and once again that assumes that the action values are not changing during the episode, but that's generally not true. Okay, and here the error at time step t is given as its return plus the expected, the approximate expected value minus the action value. Okay, and here is the algorithm for the tree backup and step tree backup algorithm. Okay, and finally, we can unify all the algorithm we considered in this chapter, and this is called Q sigma algorithm, and it is not an improvement over the previously considered algorithm. It's just a way to think about it in a unified way. And I think that this backup diagram should kind of highlight all the differences we have here. So let's compare it. So here is four-step Sarsa with an importance sampling. Here is a tree backup, first-step tree backup, and you see here we don't have any kind of importance sampling. Instead, we take an expectation of all the actions that were possible from this state. Yeah, and obviously this is kind of better, but also computationally much more expensive, right? And here you can see a generalization of it. And we have here a value sigma, which kind of indicates for us what to do, whether to do a sampling or to use an expectation. And we can, and this sigma can be kind of anything. It can be periodic as it's shown in this backup diagram, but it can also be kind of say take expectation every 3 steps, or sample every with probability like 0.5, or and take expectation with probability 0.5. So it can be very, it can be kind of different. And yeah, so here are those equations for that kind of generalized form of everything we discussed before. So here we have sigma times rho plus 1 minus sigma times the probability of action t. So when sigma is 1, we will have 0 here, and this equation will become like an update for the case of importance sampling, right? And if we have 0 sigma, then this equation will become a tree backup equation. Okay, and yeah, in general, here how it is shown in the algorithm here. Let's see. So we, in this case, we are kind of at each time step, we are selecting a sigma, and where is it? So it should be, yeah. So we select a sigma, which is between 0 and 1, And as we discussed, that when in extreme cases, when sigma is 1, it's like doing a sampling, and when sigma is 0, it's like doing a full, taking a full expectation. And yeah, we store this importance ratio at each time step. And finally, we will weight our update by this linear combination of sigma and 1 minus sigma, right? So that is Q sigma algorithm. Okay, and you can see that also, although this is kind of much more flexible and expressive, it is also requires more memory and more compute. So there is certain trade-off between like expressiveness and the algorithmic complexity here. Yeah, so that is our n-step bootstrapping, and we are moving towards the end of the table method part of the book. And yeah, so we will get to the approximate solution method in 2 weeks. So that is really interesting. So we will, because kind of I think that all the deep learning involved in reinforcement learning comes here in this approximate solution methods. So, and also notice that in chapter 12, we will talk about the eligibility traces, which is kind of another algorithmic approach to the same kind of solution of unification of Monte Carlo and temporal difference, one-step temporal difference methods, but it allows for online updates, so online learning, unlike here, unlike the Monte Carlo methods. So that is also pretty handy, and it reduces kind of the memory requirements associated with n-step bootstrapping. So that will be also interesting. Okay, so let's proceed with any questions, comments, and ideas you can have about all the stuff we discussed here.
I thought it was very good. Thanks, Ardo. It was very clear. So.
Yep. Thanks, Ardo. That was excellent.
All right. Thanks. So thanks for your attention. And I will expand my experiments a bit with this stuff and share the notebooks again. And yeah, let's maybe we can I think the next chapter is more like theoretic or summarization of stuff we learned in this part of the book, and we will maybe also have a chance to have a look at some implementations. Right.
Unfortunately, I'm not here for the next 2 weeks. I'm heading away, so I'll be missing the next 2. So I think I'm back the first weekend in September.
Oh, cool. So we probably will be back for the most interesting stuff when we start
Yeah.
with the approximate methods.
Yep.
Cool. Okay, goodbye everyone. Thank you for participation, and yeah, see you next time.
Yeah. Thanks for that, Ardo. Cheers, everybody. Yeah. So see you in a couple of weeks.
Cheers. Thanks.
See you later.
Thanks, Otto.
Bye.
Bye.